Good morning. In this video, I am describing the physical chemistry chapter Electrochemistry from Pradeep's book published by Dr. S.C. Khetrapal. The topic of the chapter Electrochemistry is pH and pKa. Definition of pH. We know that a solution may be neutral, acidic, or alkaline. The ionic product of water Kw is equal to H3O positive into OH negative is equal to 1 into 10 raised to the power minus 14 at 298 Kelvin. Always holds good. Thus, if H3O positive ion concentration of a solution is known, OH negative ion concentration is automatically fixed. Thus, to express the acidity or alkalinity of a solution, it is sufficient to express only the H3O positive ion concentration. Since the product of H3O positive and OH negative is always 1 into 10 raised to the power minus 14, the concentration of H3O positive ions may vary from 10 raised to the power 0 from for example 1 molar to 10 raised to the power 14 molar. Thus a solution may have hydronium ion concentration is equal to 2.5 into 10 raised to the power minus 5, or which may be written as 0.000025 m. Obviously, such a method of expressing the hydronium ion concentration is quite uh, cumbersome. Sorensen in 1909 suggested a convenient method of expressing the hydronium ion concentration in terms of pH. The symbol has been taken from the Danish words potens dehydrogen ion, which means the power of hydrogen ions. The following different definitions of pH are used to express the hydronium ion concentration. pH of a solution is defined as the magnitude of the negative power to which 10 must be raised to express the hydronium ion concentration. Thus, if in a solution H3O positive ion concentration is equal to 10 raised to the power minus x, next pH is equal to x. However, this definition can be used only where the hydronium ion can be expressed as a power of 10. In many cases, it may not be easy to do so. For example, a solution may have hydronium ion is equal to 2.5 into 10 raised to the power minus 5 molarity. A more general definition may be arrived at from equation 1. Take logarithm on both sides of equation 1. Log H3O positive is equal to log 10 raised to the power minus x is equal to minus x, and we get pH is equal to minus log of H3 positive. This is most common form used in numerical problems. Thus, pH may be defined as negative logarithm of hydronium ion concentration. And equation 2 may be written as pH is equal to log into 1 by hydronium ion concentration. pH may also be defined as logarithm of the reciprocal of hydronium ion concentration. Next is pH scale. Theoretically, a solution may have any hydronium ion concentration and hence may have any pH value. However, practically, the solution having H3 positive ion or OH negative ion concentration more than 10 raised to the power 0 and hence OH negative ion or H3 positive ion concentration less than 10 raised to the power minus 14 m are not common. This is because such solutions are not easy to obtain, and moreover, as the concentration increase, the degree of dissociation of the acid or base decrease enormously. Hence, the pH range is taken as 0 to 14 for most of the practical purposes. The acidity or the alkalinity of a solution may be represented on the pH scale as follows. In the middle, where the pH is 7, it is neutral, and from 0 to 7 acidic correct, and from 0 to 7 and from 7 to 14, 7 to 14 basic character increase, and from 7 to 0 acidic character increase. Next, pKa and pKb values. Just as we have pH is equal to minus log of H positive, similarly we have pOH is equal to minus log of OH negative, and pKa minus log of Ka, and pKb minus log of Kb, and pKw is equal to minus log of Kw. where Ka, Kb represent ionization constant of the acid and the base respectively. Kw is ionic product of water. Greater the value of ionization constant of the acid or the base, smaller is the value of the pK and pKb, and stronger is the acid or base, and vice versa. Thus, the larger the value of the pKa and pKb, weaker is the acid or the base. For example, if two acids Ha1 and Ha2 have ionization constant Ka1 and Ka2, 10 raised to the power minus 4 and 10 raised to the power minus 5 respectively, then Ka1 is greater than Ka2. Acid Ha1 is stronger than Ha2 in terms of pKa values. pKa1 is 4 and pKa2 is 5. A relationship between pH and pOH. pOH is equal to minus log of OH negative, since H3 positive into OH negative is equal to Kw is equal to 10 raised to the power minus 14 at 25 degrees Celsius. Log H3 positive plus log OH negative is equal to log Kw. We taken logarithm in this step on both sides. And finally we get pH plus pOH is equal to pKw is equal to 14. Next, relationship between Ka and Kb or pKa and pKb values. Relationship between pKa and pKb. Firstly, the relationship between Ka and Kb. Ka into Kb is equal to Kw, and pKa plus pKb is equal to pKw, and which further is equal to 14. Next, limitation of pH scale. The pH values of the solution do not give the exact idea of their relative strength. For example, a solution of pH is equal to 1 has hydrogen ion concentration 100 times than that of the solution of pH 3 and not 3 times. B point is A 4 into 10 raised to the power minus 5 NHCl solution is twice concentrated as compared to 2 into 10 raised to the power minus 5 normality HCl solution, but the pH values of these solutions are 4.4 and 4.7 respectively and not double. And the next point is pH is equal to 0 is obtained in one normality solution of a strong acid, and for concentration 2 and 3 and 10 and etc. the value can be negative 2. Similarly, for a concentrated solution of a strong base whose greater than 1 molarity, pH can be greater than 14. Third point is a 10 raised to the power minus 8 molarity solution of acid cannot have pH is equal to 8. The value will be close to but less than 7. Similarly, 10 raised to the power minus 8 molar NaOH solution cannot have pH is equal to 6. The value will be close to 7 but greater than 7. Effect of temperature on pH of neutral water. It may be remembered that Kw is equal to 10 raised to the power minus 14 only at 298 Kelvin, and hence pH is equal to 7 for neutral water only at 298 Kelvin. As temperature is increased, dissociation of H2 molecules increases, producing larger amounts of H positive ions. H positive increases and becomes is greater than 10 raised to the power minus 7. Hence pH is less than 7. Higher the temperature, greater is the dissociation of H2 molecules, higher the concentration of H positive ions, lesser is the pH than 7. Thus pH of neutral water decreases more and more than 7 as temperature is increased. However, as at any temperature H positive is equal to OH negative, water remains neutral. A few interesting results are given below. First is at 273 Kelvin, Kw is equal to 10 raised to the power minus 15. pH of neutral solution at this temperature is equal to 7.5 and pH scale is 0 to 15. Second point, at 333 Kelvin, 60 degrees Celsius, Kw is equal to 10 raised to the power minus 13. pH of neutral solution is 6.5 and pH of range is 0 to 13. And the next point, at the temperature of the human body, which is nearly 37 degrees Celsius, pH of neutral solution is 6.8. Measurement of the pH. Though accurate measurement of pH of a solution is done with the help of an instrument called pH meter, approximate pH with range 0.5 can be determined with the help of pH paper, which show different color when dipped in solution of different pH. Buffer solution. Definition. It is sometimes necessary that a solution of a definite pH be prepared and stored. The preservation of such a solution is even more difficult than its preparation. If the solution comes in contact with air, it will absorb carbon dioxide and becomes more acidic. If the solution is stored in a glass bottle, the alkaline impurities present in glass may dissolve into the solution and may alter its pH. A buffer solution is defined as a solution which resists any change in its pH value, whose pH remains practically constant even when small amount of the acid or base are added to it. And types of buffer solution. two types of buffer solutions are solution of single substance and solution of mixture. Solution of single substance, the solution of the salt of weak acid or weak base. For example, ammonium acetate act as a buffer. Solution of mixture is for the two types, acidic buffer and basic buffer. Acidic buffer, it is a solution of a mixture of a weak acid and a salt of this weak acid with a strong base. For example, CH3COH plus CH3CONA. Basic buffer, it is a solution of a mixture of a weak base and a salt of this weak base with a strong acid NH4OH plus NH4Cl. Next is buffer action. The property of a solution to resist any change in its pH value even when small amount of acid or base are added to it is called buffer action. The buffer action of different types of buffers may be explained as follows. Buffer action of ammonium acetate solution. Ammonium acetate, like all other salts, is almost completely dissociated into aqueous solution. CH3COONH4 uh, gives us CH3CO negative plus NH4 negative. There is excess of CH3CO negative ions and NH4 positive ions in solution. When a few drops of an acid are added to the above solution, the H3 positive ions given by the acid combine with the CH3CO negative ions to form weakly ionized molecule of CH3COH. Thus, the hydronium ion concentration of the solution does not change practically, and hence the pH of the solution remains almost constant. Similarly, when a few drops of a base are added to the above solution, the OH negative ions given by the base combine with the NH4 positive ions to form weakly ionized molecules of NH4OH. NH4 positive plus OH negative gives us NH4OH. The OH negative ion concentration and hence the H3 positive ion concentration or the pH of the solutions remain almost constant. On the contrary, the solution of the substance like NaCl cannot act as a buffer because NaCl dissociates completely to give Na positive Cl negative ions. These may combine with the base or the acid added to form NaOH or HCl, but these ionize completely to give back the OH negative ions or H3 positive ions. Thus, the H3 positive ions concentration of the solution changes and the pH of the solution changes. Buffer action of acidic buffer. For example, let us consider the buffer action of the acidic buffer containing CH3COH and CH3CONA. Acetic acid dissociate to a small extent, whereas sodium acetate is almost completely dissociated in the aqueous solution. By common ion effect, the ionization of CH3COH is further suppressed. Thus, in the solution, there are excess of acetate ions and a small amount of hydronium ions. When a few drops of an acid are added to the above mixture solution, the H3 positive ions given by the acid combine with the CH3CO negative ions to form weakly ionized molecules of CH3COH. CH3CO negative plus hydronium ion gives us CH3COH plus H2O. Thus, hydronium ion concentration and hence the pH of the solution remains almost constant. Similarly, when a few drops of a base are added to the OH negative ions given by the base combined with the hydronium ions are already present to form weakly ionized molecule of H2O. As the hydronium ions are consumed, the equilibrium shift towards right according to Lerchitler principle. Thus, more of the CH3COH dissociate to make up the loss of hydronium ions. Hence, the hydronium ion concentration of the pH of the solution does not change. Buffer action of basic buffer. For example, NH4OH plus NH4Cl may explained as follow. NH4OH dissociate to a small extent, whereas NH4Cl dissociate completely in aqueous solution. By common ion effect, the ionization of NH4OH is further suppressed. In the solution, there are excess of NH4 positive ions and small amount of OH negative ions. When a few drops of base are added, the OH negative ions gives by it immediately combine with NH4 positive ions to form the weakly ionized NH4OH. NH4 positive plus OH negative give us NH4OH. The hydronium ion concentration of the pH of the solution remains unaffected. Similarly, when a small amount of acid is added, the hydronium ions give it by its combine with the OH negative ions already produced NH4OH in equilibrium. H3 positive plus OH negative give us 2H2O. As the OH negative ions are consumed, the equilibrium shift in the forward direction. Thus, more of the NH4OH dissociate to produce more of the OH negative ions, which makes up the loss of the OH negative ions. Hence, the OH negative ion concentration. Therefore, the hydronium ion concentration or the pH of the solution remains fairly constant. Retain in memory the buffers as explained above are weak acid buffers, pH range 4 to 7, and weak base buffer pH range 7 to 10. However, solution of strong acid like HCl, HNO3 of suitable concentration also act as buffer with a low pH, and a solution of strong base like NaOH, KOH of suitable concentration also act as buffer with a high pH. A strong acid buffer. A strong acid is completely ionized in the aqueous solution, and hence H positive ion concentration is very high. The addition of a small amount of the acid or base has negligible effect on the pH of solution. For example, addition of 1 centimeter cube of 0.1 molar HNO3 to 100 cc of 0.01 m HCl changes its pH from 2 to 1.96, which is negligible change. Strong base buffer. A strong base is completely ionized in the aqueous solution, and hence OH negative ion concentration is very high. The addition of a small amount of acid or base has negligible effect on the OH negative ion concentration, and hence the H positive ion concentration of the pH. For example, addition of 1 centimeter cube of 0.1 molar HCl to 100 centimeter cube of 0.01 molar NaOH solution changes its pH from 12 to 11.96, which is negligible changes. Calculation of pH of buffer mixture. Henderson-Hasselbalch equation for acidic buffer mixture. The equation is pH is equal to pKa plus log salt by acid. The next equation is pH is equal to pKa plus log conjugate base by acid. And for basic buffer is POH is equal to pKb plus log salt by base. And pH is equal to pKa plus log into base by salt. pH is equal to pKa plus log into base by conjugate acid. Next, buffer capacity or buffer index. Buffer capacity is equal to number of moles of the acid or the base added to 1 liter of the buffer is divided by the change in pH is equal to dN by d into pH. Buffer capacity of a buffer is maximum when the concentration of the weak acid and its salt or weak base or its salt are equal. When pKa is equal to pH is equal to pKa or POH is equal to pKb. Importance of buffer solution in biological process. The pH of our blood is maintained constant at about 7.4 in spite of various acid and base producing reaction going in our body. In absence of its buffer nature, we could note it a variety of foods and spices. The buffer action is due to the presence of the carbonic acid and bicarbonate ion and carbon dioxide in the blood. In industrial process, the use of buffer is an important part of a many industrial process in electroplating in the manufacture of leather, photographic material and dyes, in the preservation of food articles, in analytical chemistry, in the removal of the acid radicals such as phosphate, oxalate, borate, which interfere in the precipitation of radicals of group 3, Al3 positive, Fe3 positive, Cr3 positive of salt analysis, in complexometric titrations, metal ions with ADTA, and to calibrate the pH meters. In bacteriological research, culture media are generally buffered to maintain the pH required for the growth of the bacteria being studied. Formula used for numerical problems. By Henderson equation, pH of an acid buffer is given by pH is equal to pKa plus log into salt by acid. Similarly, for basic buffer, POH is equal to pKb plus log into salt by base. Plus the next formula is pH plus POH is equal to 14, and pH is equal to 14 minus POH. Thank you.